Last time we were talking about sensitivity of the loudspeaker and how the amplifier power is multiplying to the perceived sound levels. See, it's a transducer. Transducer means it converts one type of energy to another loudspeaker. So it's in here. It converts electrical energy to acoustical energy, or it's a form of mechanical energy, but it is very inefficient. Only 1 to 3% of electrical energy is actually converted to sound. That is one of the reason that 10 dB, 3 dB difference we are seeing it. This also attributes a lot of to that. So once we have a loudspeaker driver, we need to make up for this inefficiency a bit. Like we have to compensate for the inefficiency in some way or the other. So we use different type of enclosures. To build the enclosures, we need to know that how these electrical and mechanical parameters, parts of the speaker work. So there are pioneering work done by two scientists. And these parameters are mainly known in their names, Thiel and Small. So this speaker has, this is the magnetic, this is the magnet, this is the mainly the motor of the speaker. This is the mouse. The motor consists of the coil and the magnets around it, and there is a pole piece which is inside. This is the main heart. It's the engine that drives the motor. And the cone is suspended using a spider, and there's a surround. So the purpose of this spider and the surround is to ensure linear motion. See, when a membrane is vibrating, suppose a drum is vibrating, that vibration is entirely different from how a speaker works. Speaker translate that only into linear motion. If in a way you are talking about turntables before, turntables have groove. So everything is voltage difference, it is recorded in that way. So for say 40 hertz, the distance the cone needs to travel is different from say 150 hertz. So and sound is actually, it is not that once a 150 hertz comes, 40 hertz is not there, 40 hertz is also not there, 150 hertz is also not there. So it happens so fast. It is not that you get 140 hertz happening and then woofer cones comes to rest, and then it is not a perceivable difference. We cannot just consider it as a slow action as such. All these, what the motor does is when the power goes through it, current pass through it, it gives the command, like it gives the power, it moves in the magnetic flux according to the amplitude of the signal. Basically, this line, this grooves, what I was talking about, the pistonic motion. Okay. And when the cone is set into motion, it has a tendency to vibrate. It is made up of this suspension and a spider. This spider and the surround, it actually brings it back to an equilibrium. It has a tendency to bring it back. So these two are opposing forces. The force that drives the cone and the force that comes in, and the resistance that is given by the mechanical surrounds, the surrounds and all. So the Fs is the free air resonant frequency is the, let me see if I can put it in a different way. I must say I'm using the wrong presentation here. That's what happened. I could not go to home yesterday. My presentation is in my home PC, so I am just trying to recollect. I simplified it. So just give me a moment. I'll explain it in a different way. Okay. See, when every matter, like any membrane or any material which has a natural frequency, that is what frequency it resonates. So this speakers resonate. Okay. This Fs is derived entirely from the weight of the moving parts. Okay, it includes the weight of the cone, it includes the weight of the surround, it includes the spider, everything, and it actually for low frequency speakers, the Fs will be very low. It will be like subwoofers and all. It will be something like 20 hertz, and as the for mid woofers, it will be something like 45 hertz, and for full ranges, it can go up to 70 hertz. So it varies like that. But once the cone is set into motion, the surround and the spider brings it back. So that, in other way, is called the damping. Damping is very important when you consider the quality of the sound of the speaker. Like when we and there is something called a Q factor, which actually explains the damping, relative damping of the speaker. So the Q is there are three Q factors. One is the total Q, that is the QTS. Then there is QMS, that is the quality of the mechanical suspension, that includes the spider and the surround. And then the quality of the electrical suspension, which includes is the motor system. So these two factors actually control the total Q, total quality of the total damping of the speaker at resonance. In other words, when we say if a speaker has a high QMS, it will be very solid. Like it is a solid build. It's a smooth suspension. The compliance will be also more normally. Okay, maybe I will come to that more later. Then we have CMS. CMS is the compliance of the mechanical suspension, which is actually inverse of stiffness. The surround is stiff. For full ranges and PA speakers, the surround is normally very hard. But as it goes to subwoofers, you can see it is very compliant. You can say the speakers is very compliant. It is smooth. Then there is an important factor known as VAS. VAS is actually when the speaker vibrates at its Fs. It has a springiness. Right? That springiness is converted when okay. VAS is the amount of air which has the same springiness as the membrane at Fs. Okay. Then we have the MMS, which is actually mass of the moving parts of the driver. It includes the mass of the cone, coil, and the air in contact with the cone. Then impedance. Impedance is actually actual resistance, it is actually AC resistance. It varies according to frequency. It is not, when you say speaker's impedance is 4 ohms, you need to know which frequency, like which is the intended frequency range. When we say 4 ohms, for a subwoofer, if it is 4 ohms, it will be from say 20 hertz to maximum 150 hertz is where it will be 4 ohms. But for a 4 ohm speaker, the actual resistance, DC resistance will be something like 3 ohms or 3.5 ohms. Actually, how the impedance happens is, impedance is happening due to a property which is known as inductance. Like now, when actually the cone is moving in the magnetic, there is a back EMF produced, and that actually resists the flow of current. Okay, so the actually resistance increases. If you see the impedance plot of a driver, you can see that the resistance will go like from here, and at Fs it will be at a peak. It is because at Fs the speaker has a natural tendency to vibrate, so the amplitude of vibration will be more. That means more back EMF is produced, so more resistance. Then another is the Xmax. Xmax is the maximum linear excursion of the cone within the gap. Then there is maximum continuous power handling capacity. That is the rated watts, what we say, rated maximum power handling. And there is BL. BL is the magnetic strength. If you have more BL, the BL value is high. That means the very strong motor system. So when a speaker is manufactured, it will have an intended role. So this intended role on which enclosure it can be used. The manufacturers actually give specs, like for specs they will say you can use it in a BLH, or it can be used in a MLTL or a seal box. You can, if it is not given, you can actually use a method called as, you can use this method to determine which enclosure it will be more suitable for the driver. It is actually calculated, it is known as efficiency bandwidth product, which is calculated by dividing Fs by QES. Fs is the free resonant frequency, and QES is the quality of Q factor of electrical suspension. Basically the motor strength and the tendency of the speaker to vibrate. So these are the factors that matters. This actually this needs to be taken as a rule of thumb, because speaker, when you keep it in an enclosure, it ceases to be a speaker. It is actually the speaker system that actually emits. So it's a combination of a lot of other parameters. As a rule of thumb, you can use, suppose your EBP is less than 50, it will be more suitable for sealed enclosures. And then if the EBP is between 50 and 80, it can be used for, it is basically the all-rounder. Can be used for sealed, ported, OB, TL, etc. Then 80 to 100, it's more suitable for ported. And above 120 and 150 is more suitable for horns. Then again, coming back to the QTS, when we purchase, we wanted to, we are looking for specs, mainly Madison, we see a lot of drivers. How will we define which is good, which is not good, or which more suitable for the purpose of use? Some general pointers are this: if the QTS is low, QTS low means it motor has more control over the cone movement. QTS 0.2 means usually it will have a large magnet. It has a very good control over the cone. It matters because as I said, like when a signal goes through, there are 40 Hz component, there are 150 Hz components. So it is necessary that once the 40 Hz motion is initiated, Vistonic motion is initiated, it has to come back. So the damping, the motor asks the cone to come back. If the cone is not coming back, you get a different feel. That's what I call now the heavy sound, tight sound. All those things happens there in that area. So if QTS is low, usually you will get tight sound. What you call now. You hear. All these years I have never heard drums as the same timbre as in a speaker. I never heard it. So far it is not possible, but the closest is the PA speakers, I can tell. The closest you will get is a stiff surround, high QTS, low QTS drivers which are more faithful to that transients.
You should listen to Anil's Altex. Hear a drum transient as it is.
Yeah. Then when it comes to our normal speakers, the 0.45 is the QTS we will normally find. Almost all commercial speakers will have a QTS of almost 0.45. It translates to, that's one of the reasons we cannot, we don't get the bus correctly. We will get mostly maybe the records are mastered in such a way, I don't know. Like it anyway, it actually sounds different. You don't. 0.45. I am not a big fan of 0.45 QTS. Mainly in the. This is a personal thing. Okay, when it can be a different reviews coming. But what I have noticed is from 100, we say bass, but below 40 or below 80, it is not much of a problem. If you increase, if you have an active system, if you crank it up, you can probably compensate for that. But 100 to say 200 hertz, that is where where the transients, this 0.45 QTS will make everything boom. You can hear muddy sound. It actually muddies a lot of that transients of drums, everything. It muddies. You get even the everything is associated with a boom. It never stops. It is an extended boominess you hear in that those areas. I have not found a 0.5 or above driver which does faithfully reproduce that part of it. Okay, now, and there was one question about low sensitivity drivers. Low sensitivity drivers, if we have a driver which has a FS of say 30 Hertz and the sensitivity is 98 dB, and another driver with same FS or maybe lower FS with 86 dB. Obviously the high sensitivity driver is much better choice. But if for some reasons we cannot accommodate that, suppose that driver is a big one, or mostly that is one of the reasons we cannot go for those high sensitivity drivers. Then low sensitivity drivers, the Xmax is one thing we need to look into. Suppose because how they compensate for the low sensitivity, we need to crank up. So we need to have more movement, cone movement. So that is one pointer. If okay,
is Xmax both ways or one way?
Xmax is the one way only.
One way.
It goes up
Till the coil leaves the gap.
and come back. So overhang actually, it's not the.
It's the same amount of coil in the reverse direction.
Actually, we can peak to peak.
Minus.
No, there is a little bit of travel, but basically the equilibrium, the damping works to stop at the equilibrium. It will not go down. The bottoming happens, then there is a problem. The current, the motor asks the coil to go down, what will you do? Yeah. And now it comes to all Anil's and adjusted drivers with low MMS and powerful motors. Yeah, that means that have the better transient response and the heavier cone. Okay, heavier cone, what I meant is like all these car speakers and all, you've seen that heavy thick cones and thick motors, but still the transient response won't be as good as this. What they're trying to do is I think it's a trade-off. No, they try to increase the mass MMS, try to reduce the FS like that, and compensate on the BL, maybe the motor strength. Okay. Now we just have a quick go through all those type of enclosures that we use. The sealed enclosure is one of the very simplest thing to make for a DIY for enthusiast. It is just a closed box, but with a very small hole in it to keep, minute hole. That is actually to have a pressure. You need a small hole. This I forgot the correct word for it. Okay. Atmospheric pressure matching. Okay. And when you keep a speaker in a enclosure, the Q factor actually changes. If you have a 0.2 QTS speaker and you place it in a box, Q increases actually. It will not reduce, it will increase. So which is the actual Q, which is the ideal Q that we look for, is 0.707. This line is the transient response to the system of 0.707 Q. And as you can see that when the QTZ is going above, the transient response is bad. Like it actually booms. It attacks first and then comes. Right. Then we have next two common systems are the ported ones and the passive radiators. Ported, I'll go one more one. When you play, I'll go back to this one thing I need to mention. When you keep a speaker in a closed box, the air enclosed will act as a spring. Basically, it's a spring, and it will have a natural frequency also. It will have a resonant frequency, and this resonant frequency determines the lowest cutoff that we can get from the speaker. Okay, when it comes to the ported ones, see this area, all this air contained in this area will have a resonant frequency, and you will have there is air trapped in this tube, which has a mass. The amount of air trapped in this area will actually reduce the resonant frequency. It will actually control the resonant frequency of the air trapped inside. Okay, when we keep a very long cord, you tune it low. Same conduct. Right? Or you can just consider it as a spring. If you have a spring and you vibrate it, it will vibrate at its resonance. You hang a weight to the spring, it vibrates as a low frequency. It's the same principle applied here. Passive radiator is also the same principle. In which the membrane, the cone with the suspension acts as the which controls the resonance of the air inside. So in passive radiator, what you do is you actually add mass to the cone. You will have most of the passive radiators will have a screw, and with weights you can add, and actually that is how you tune the passive radiator speakers. And then comes this is a transmission line and mass loaded transmission line. Transmission line is also ported. It's a ported one, but in this case what happens is there is a property of the sound wave inside that is called as quarter wave resonance, that is taken into consideration. Quarter wave resonance, see this is one. Here to here is a full wave, right? So here to here is a full wave. you can see that in this quarter wave the amplitude is quarter wave the amplitude is the highest. So when a sound when a air is oscillating inside the enclosure, this quarter wave notes will be very pronounced. We can actually use that resonance to enhance the frequency, enhance the output basically. So quarter wave is actually quarter of the wavelength. Suppose the wavelength is say 1 meter, quarter wave frequency will be 250 mm. So what transmission line does is, it will actually have a very long tube and the driver is attached to one end, or it can be a ratio between from the one tape to control the resonance behavior of the air column inside. The idea is to make sure that you wanted to extend the low frequency to the maximum. At the same time, you don't want any other resonance node interfering with that. So for that, you can use padding to soften out those resonance peaks. So the padding will not be as it may not be as uniform as this. We can actually calculate and see, okay, say I am tuning for 20 hertz and I see that it has a very 20 hertz is the 20 hertz will be the tuning frequency here. But what will happen here? It will be something like 150 hertz will have a strong quarter wave peak here. So what will I do? We need to damp it. So you can actually increase or decrease the density of the material here to control those resonances. Otherwise what will happen is these different amplitude signal will actually hamper the strength of the 20 hertz that is coming out of this tube. So this quarter wave, when we consider this quarter wave resonances, you can actually operate the driver at a very low frequency as well. Like suppose even the Fs is high. Normally when you put a driver in a ported box, suppose the Fs is 40 hertz, regular ported box you can bring it down to say 10-15 hertz below. That is a normal, that is what you can normally do, but quarter wave resonance we can bring it, quarter wave transmission lines and all, we can bring it significantly low, like say 25 hertz. But I did some testing. I still think that size matters. I mean, like when it comes to low frequencies, these small drivers, yes, but okay, if you have a high Xmax driver, that again counts. If your small driver is having some Xmax, like say 15 mm, yes, you have a 6-inch speaker, it can move 12 to 15 mm of Xmax. Then you put it in a transmission line, it can touch say 30 hertz. Easily you can actually get some SPL from that.
Then what happens to the high frequencies? How does that sound?
High frequency sound is anyway directed. You have wadding coming all the way here. So all the high frequency will be absorbed by the time it reaches.
15-inch Xmax on a 6-inch driver. And then the high frequency modulation.
High frequency. No, but
he is telling about a single driver.
Single driver. I don't think.
How will you take? Okay, 6-inch driver, you will cross at 3 kilohertz. Then above 800 hertz, you will start hearing.
No, but again, transmission line we are using quite an amount of absorbing material inside. So the airwave at high frequency, it will be attenuated to an extent. It will not come. But it will be a problem in a ported box. Suppose you use a ported box and use a high Xmax driver, and as well you will have a lot of high frequency content coming through the port. It will happen.
Anthony, you mentioned about resonances like at different frequency to damp that. How do you find out those resonances, modes, or whatever?
You can actually calculate according to the distance, quarter wave distance. You can just say it's like mu is equal to f by lambda, f by lambda. I forgot that. Yeah, spreadsheets are there. Just get the frequency divided by 4. Like I said, say 400 hertz, quarter wave frequency will be, quarter wave length will be about 252 mm. So if you have 252 mm comes here and 400 hertz, actually it's a trial and error. You need to see how much, mostly anything below 400 hertz, the attenuation is not that good. You need to depend mainly on the damping of your speaker. You can't do anything. I'll say you can't do anything at all. All this damping, everything will look good, it will hold good when the frequency is above 400. Otherwise, then what is happening other than that is when you increase you reduce the volume of the air inside and you actually increase the viscosity of air. So the property is slightly different. I mean, it is not exactly, yeah.
Is the absorbent material, is it chosen